Hi, my name is Sohan Paul, and this is my Physics 2 Lab 2 Charge Tapes Revisited. The purpose of this lab is to build off the last one, but more accurately model the pieces of tape by considering them as multiple evenly distributed point charges, and we'll do the entire experiment through goal script modeling. The new estimated charge is supposed to be 1 times 10 to the negative 8 coulombs, as opposed to the old charge which was calculated to be 3.39 times 10 to the negative 9 coulombs. This is almost an order of magnitude higher, and we'll explain why.
We can justify these results to three fundamental principles. First, Newton's second law, which states that the net force on an object is equal to its mass times net acceleration. Coulomb's law, which essentially represents the electric force between two objects along a line in between them, proportional to the charges themselves and inversely proportional to the square of the distance between them. And gravitational force, where near the Earth's surface, its mass times 9.8 meters per second squared pointed downward.
To proceed with our calculations, we were given several initial conditions. We were able to measure the tape itself and then use the linear mass density of the clear tape to get the tape mass. In addition to that, we were given several physical constants, such as the gravitational constant and the Coulomb constant. And finally, we measured that the tape separated at about 0.77 centimeters of distance between them. To be more precise, let's define the system with which we considered results. The system was considered tape B, and the surroundings that were acting on tape B were tape A and the Earth. The main difference in our model is that the electric field at each point on tape B was comprised of the addition of the electric field vectors due to each of the point charges on tape A. Due to the superposition principle, we were able to add these vectors together to consider the net electric field on each charge on tape B. The charge of each of these point charges was the charge of the total tape divided by the number of sections or point charges that we dictated. The glow script model allowed us to easily compute these vector additions on each point charge at tape B, as well as rapidly change two main parameters: the number of point charges on each tape, as well as the overall charge on each tape. Doing so allowed us to find the final magnitude of charge on each tape such that for 10 point charges, we could balance out the magnitude of the gravitational force and that of the electric force. And as you can see, we got pretty close, around 0.2 e to the negative 3 newtons. The difference between our new glow script model and the old glow script model for Lab 1 are numerous. Instead of considering each tape to be a point charge, we're now considering each tape as a line of n equal point charges spanning the length L. Additionally, instead of calculating the magnitude of charge on each tape, we are now estimating externally and then splitting the charge evenly across these n sections. Further, we're considering the electric field on each section of tape B as a superposition from all n elements of the other tape. We compute the force as a pairwise sum, and then compare the magnitude of charge needed to balance out the electrical and gravitational force as opposed to calculating them directly in Lab 1. The accuracy of this lab experiment is better for finite length geometry and edge effects because the electric field at each section of tape B is not the same or uniform. However, the Lab 1 point charge consideration is better if the distance between the tapes is a lot bigger than the length of the tapes themselves. Although our new glow script model is more accurate than the old one for point charges on the edges of tape B, we still make some considerable assumptions that provide sources of error. For example, we assumed each piece of tape to have an equal magnitude of charge across the tape. We divided the magnitude of charge evenly across each section. However, each piece of tape was handled differently and imperfectly, and it's likely that one of the tapes lost more charge than the other across the different sections. If each tape was modeled as a point charge, the model would assume that all charge is concentrated on one spot, so it would overestimate the electric push for a given Q. Because of this, the model would essentially predict a stronger force than the real spread out tape, so it would essentially predict a smaller Q value than what it was actually. The line or distributed model treats each tape as multiple small charges along its length and adds their contributions by superposition. These estimates differ because in reality most charge pairs are farther apart than D and not directly above or below one another, so each contributes less to the upward force and the side components partially cancel. The real net force between the finite tapes is weaker, so to balance out the magnitude of gravitational and electrical force, the Q would be larger.